Okay, let's wrap up this section on inverses by talking about the domain and range of an inverse. They actually have a unique relationship. The domain and range of a function and its inverse just swap values. For example, suppose f of x has a domain 0 to infinity and range 2 to 5. Then the inverse will have the domain 2 to 5, oh, that should be a parentheses, should have the domain 2 to 5 and range 0 to infinity. So that's always true with inverses. Now, remember a while ago we found the inverse of this function and we determined that it was this function up here. So let's put these two functions in a little table here. Now, it's easy to determine the domain of this function. So the domain of this function, since 3 would make the denominator 0, we know that x cannot equal 3. Okay, now in interval notation, that means we go negative infinity to 3, union 3 to infinity. Okay, now the domain of its inverse, if you do the same thing, the domain of the inverse, we know that 1 plus x cannot be 0, so that means x cannot equal negative 1. And the interval notation would be negative infinity to negative 1 union negative 1 to infinity. Now, since the domain and range of a function and its inverse just swap places, then all I have to do to find the range of f is look at the domain here of the inverse. So since the domain x can't be negative 1, then the range of its inverse must be that y cannot be negative 1. And if I want to find the range of this inverse, just look at the domain of the original function. The domain of the original function says x cannot be 3, so the range of its inverse must be that y cannot be 3. And of course you can also write the interval notations for that. So, you know, that's an important aspect of this, is that the domain and range of a function and its inverse just trade places. Now, of course, when you define the domain, you use x. When you define the range, you use y. Something else you might find interesting about a function and its inverse, like these two here, if I were to say pick 3 points off of, say, the first one or the second one, really doesn't matter. Let's say the blue graph. Let's say I pick 3 points on the blue graph. This point, negative 2, 5. This point, 0, 1. And this point, 3, 2.5 is on the blue or purple, whatever color you want to call that graph. Well, what's interesting is if you just reverse the x and y's in each of these, you'll also find a point that's on its inverse. So watch what happens. If 0, 1 is on this graph, then 1, 0 is on its inverse, right? Okay, if negative 2, 5 is on this graph, then 5, negative 2 is on its inverse. If 3 and 2.5 is on this graph, then 2.5, 3 is on its inverse. So basically, you know, that kind of goes along with the fact that the domain and range just swap places. So, you know, all of the corresponding ordered pairs in the form x, y become the same corresponding ordered pairs, but the x, y just trade places. The last thing I wanted to show you is I wanted to show you an application of inverses. Encryption is basically a way to hide or encode a secret message. So let's suppose I were to use the function 4x plus 11 to encode the word cable. I just randomly picked that word. It doesn't really come from anything special. Now, C is the third letter of the alphabet, A is the first letter, B is the second letter, L is the 12th letter of the alphabet, if I counted right, E is the 5th letter. So basically I could say cable corresponds to 3, 1, 2, 12, and 5. C-A-B-L-E. Well, if I were to plug these numbers into some function, let's just say some simple function like this linear function. If I plug 3 into this, I get 12 plus 11, which is 23. If I plug 1 in, I get 4 plus 11, which is 15. If I plug 2 in, I get 8 plus 11, which is 19. If I plug 12 in, I get 48 plus 11, which is 59. If I plug 5 in, I get 20 plus 11, which is 31. So I could say that these 5 numbers are the word cable encoded. So I've basically encoded or encrypted a secret message here, because these numbers don't really mean anything to most people. Okay? But if you and I were passing secret messages around, all you have to know is that I'm going to use this function here to encode the message. And remember earlier we talked about, we actually had the inverse of this function earlier, and it was actually 1/4 x minus 11/4. So if you knew that inverse, then all you have to do is take those same numbers, 23, 15, 19, 59, 31, and plug them into the inverse. Watch what happens. If I plug 23 in, I get 23/4 minus 11/4. Let's see, 23 minus 11 would be 12. 12 over 4 would be 3. If I plug 15 in, I get 15 over 4 minus 11 over 4, which is 4 over 4, which is 1. If we plug 19 in, we get 19 over 4 minus 11 over 4. Let's see, is it 19? Yeah. 19 over 4 minus 11 over 4. That would be 8 over 4. That would be 2. And then if I plug 59 in, I get 59 over 4 minus 11 over 4, which is 48 over 4, which is 12. And then if we plug 31 in, we get 31 over 4 minus 11 over 4, which would be 20 over 4, which would be 5. And there you go. And now you could decode my message and figure out that this is the 3rd letter, 1st letter, 2nd letter, 12th letter, 5th letter, and then just determine C-A-B-L-E. So it's a very simple way to use a function and its inverse to encrypt messages. And the neat thing about it is there's infinitely many functions that have inverses. So just because someone knew I used a function and its inverse to encode or decode a message, that doesn't mean that they could just randomly pick the right function. For instance, I could have used these 2 functions. I would have probably gotten fractions if I had, but I could have used this function to encode the message and then this function to decode the message. So, you know, that's just one of the applications of inverses that I thought you might find interesting. Well, that completes our lecture on inverses, and I believe the next section I'm going to get into some either quadratic functions or applications, but we'll see what the next one is.